Hi there, this is the lecture video for Chapter 9, Section 1. You made it to the last chapter. Way to go. We'll be using the T distribution table and a new table, Table 11, so have those handy. You'll also need to have your calculator close by, as you're going to learn a new function that you'll want to definitely remember. This one is an alternative to a very ugly formula, so you want to make sure that you have this one down. We also have several step-by-steps that we're going over this time, so if you have a special way that you're tracking those, you want to get that ready. Okay, this one's a doozy, but I know you can handle it. Let's dive in. Welcome to the lecture video for Chapter 9, Section 1, Correlation. We're going to cover quite a bit today. Specifically, we're going to introduce the concept of linear correlation, independent and dependent variables, and the types of correlation. We're going to talk about how to find a correlation coefficient, how to test a population correlation coefficient, rho, using a table, how to perform a hypothesis test for a population correlation coefficient, rho, and how to distinguish between correlation and causation. Let's warm up a bit with the idea of relationships. I want you to think about the following variables, and I want you to think about whether a relationship exists between the two variables. Here are the two variables, SAT scores and college GPAs. Pause the video for a moment and think about that. Is there a relationship between those variables? I would say there probably is a relationship between those two variables. People who score well on standardized tests tend to do well in higher education. Okay, let's look at another set. Think about whether these two variables have a relationship to each other. IQ and height. Pause the video for a moment and think about it. I would say probably not. There is probably not a relationship between IQ and height. How tall you are has nothing to do with your IQ score. So what we're going to be talking about today is all about how things are related. We're going to have three main goals, and they are to find out, does a relationship exist? If so, can we describe it? And is the relationship significant? So to explore this, we need some new terminology. Correlation is the relationship between two variables. In statistics, the data can be represented by ordered pairs, x, y, where x is the independent or explanatory variable, and y is the dependent or response variable. Ordered pairs are best displayed in a scatter plot, where x and y are graphed on a coordinate plane, where the exploratory variable, x, is measured on the horizontal axis, and the dependent or response variable is measured on the vertical axis. A scatter plot can reveal whether there is a linear correlation between the two variables. For example, here's a quick coordinate pair system. I have 5 x and y ordered pairs. If I were to graph these ordered pairs together on the xy plane, I could see that they have a roughly positive linear relationship. You can see that they are sloping in the positive direction, to the right and upward. Let's remind ourselves how to do this on the calculator. First, we need to enter our data into L1 and L2, x values into L1 and y values into L2. Remember how to do that? It's been a while. So you do that by pressing Stat, then Enter. If you have something already in there in one or both of the lists, arrow up to highlight the heading of the list and press Clear, then Enter, and it will clear the list for you and put you back in the top line to start entering values. So enter x values into L1 and y in L2. Pause the video now to do this. When you finish that, press the second button, then the y equals button. Then select Stat Plots menu and select 1 plot 1 and press Enter. Now arrow down and select On and press Enter to select it. Next, you're going to arrow down and select the type of graph you want, which is the scatter plot with the individual dots. Press Enter to select it. Then arrow down if needed to select L1 for the X list and L2 for the Y list. You may have to do that a couple of different ways. Some people may have to do the second button and the number 1. Other people may have to select from a list, L1 or L2, depending on your calculator. When you've done all of that, press the zoom button, then the number 9, and it should provide a scatter plot for you of all these points. Okay, so why did we do this? Well, we wanted to see the relationship between the ordered pairs, the way they were related to each other in a linear way. Let's talk about the different types of correlation. If all the points are following in a line but descending, the x values are increasing, meaning going across the horizontal axis, but the y values are decreasing, going downward. And you see this sort of downward slope. We say this is a negative linear correlation. If, however, all the points are rising to the right, like our example, the x and y values are both increasing, we say they have a positive linear correlation. Now we could just have a random assortment of points that are all over the place and don't seem to form a pattern at all, and we say those have no correlation. Or you could have some sort of pattern, like this one is more quadratic than linear. We just say they have a non-linear correlation. They could have a different type of relationship, but it is non-linear, meaning not in a line. So let's do a couple of examples where we're identifying the type of correlation that's present. A researcher wants to determine whether there is a linear relationship between a country's gross domestic product, or GDP, and carbon dioxide, or CO2 emissions. The data for 10 different countries in a recent year are shown in the table. Display the data in a scatter plot and describe the type of correlation. Okay, so yes, we're going to enter this data. I would put this in L3 and L4, put the GDP in L3 and the CO2 emissions in L4. Remember, you do that by pressing Stat and Enter. If you already have something in one of those lists, go up to highlight the title of the list and press Clear and Enter. Okay, so pause the video and enter those numbers now. When you have finished that, let's put the data in a scatter plot. We do that by pressing the second button, then Y equals, selecting Stat Plots, and then you need to make sure that you have those things selected after that. Having one plot, one on selected, having the scatter plot type selected, and then you'll need to change the X list and Y list to say L3 and L4, because now you have the data in different lists. Then press Zoom and 9, and you should have something like this. It's not exactly a line, but it does appear to have a positive linear correlation. Reading from left to right, and that's the way we do read graphs, as the gross domestic products increase, the carbon dioxide emissions tend to increase as well. Okay, let's do another example. A student conducts a study to determine whether there is a linear relationship between the number of hours a student exercises each week and the student's grade point average, or GPA. The data are shown in the table below. Display the data in a scatter plot and describe the type of correlation. Pause the video and enter these values in your calculator. The X values in one of your lists, the Y values in another, and come up with a scatter plot like we did before. Pause the video now and do that. You should have gotten something that looks like this. There does not appear to be a correlation between the number of hours a student spends exercising and the student's grade point average. There doesn't seem to be any sort of relationship between them. A correlation coefficient is a measure of the strength and the direction of a linear relationship between two variables. The symbol lowercase r represents the sample correlation coefficient. The formula for r looks a little hairy. It is the ratio of n times the sum of x and y minus the sum of x's times the sum of y's divided by the product of two radical expressions. Yes, that looks very scary. The x values are coming from the independent variable, and the y values are coming from the dependent variable, and n is representing the number of data pairs, the number of coordinate pairs in the graph. R is supposed to be the unbiased estimator of the population correlation coefficient, which is represented by the lowercase Greek letter rho, the symbol here. The range of R is actually quite limited, and kind of like with probabilities, where it sits on the range has a meaning. The range of values for the correlation coefficient is -1 to 1. The closer to -1 it is, the stronger its negative linear correlation. The closer to +1, the stronger positive linear correlation it has. If r equals -1, there is a perfect negative correlation. If r is close to 0, there is no linear correlation at all. A note here, though, there could be another kind of relationship, like the parabolic relationship we saw before. It just means there's no linear relationship. If r equals 1, there is a perfect positive correlation. Let's look at some examples. In the upper left corner, all of the points are in an exactly positively facing line, going upward. This is a perfect positive correlation. The y values are perfectly aligned with the x values, so when the x value is moving in a positive direction, the y values move in a positive direction right along with them at the same rate. R equals +1. The one right below it, on the left bottom corner, is the opposite. All the points are in an exactly negative facing line going downward. This is a perfectly negative correlation. Remember, we always read this from left to right. R equals -1. The center top one is similar to the top left one in that its points are trending toward the top, and it's clear that there's a relationship between x and y, and it's a strong relationship, but it's not exact. We would say that there is a strong positive correlation, and in fact the r value for this one is r equals 0.81, which is close to 1. So it is a strong positive correlation. This one is the opposite. We see the same thing, but in the opposite direction. Points are related and all trending downward towards the bottom, and there's a clear relationship between x and y, and it's a strong one, but it's not exact. We would say there's a strong negative correlation, and the r value is -0.92. Next, the top right one is vaguely positive, meaning you can see a very minor trending toward a positive relationship between the x and y values, but it's not strong. The r value for this is 0.45. And the bottom one has no correlation, and you can see there is no relationship between x and y, and the points are not trending in any direction. The r value for this is 0.04, very close to 0, which is what we would expect. Let's go over the steps in words and symbols, how to calculate a correlation coefficient. First, we have to find the sum of the x values. That's pretty straightforward. Next, find the sum of the y values. Again, no problem. After that, we need to multiply each x value by its corresponding y value. Then we find the sum of those products. Then find the square of each x value. Then find the sum of those squares. Then find the square of each y value and find the sum of those squares. Finally, use all 5 of those sums to plug into the formula and execute the operations as shown in the formula, using n as the number of pairs. So I'm going to talk you through the process of finding the correlation coefficient for the gross domestic product problem from before. But don't feel like you have to write notes for this part, because after I'm done, I'm going to give you a calculator shortcut. Okay, so the directions here read, calculate the correlation coefficient for the gross domestic product and carbon dioxide emissions data. What can you conclude? So in order to do this problem, we would first need to sum up all of the x values. Then we need to sum up all of the y values. Then we need to multiply the x and y values together, then come up with that sum. Next, we need to take each x and square it, then come up with the sum of all those squares. After that, we square each of the y values and come up with the sum of those. Finally, we take all 5 of those sums and we use them and n, the number of xy pairs, to plug into the formula. Now, if you do all that perfectly and get everything exactly in its right place into this awkward looking formula, you will get the value of r, the correlation coefficient. You do all that perfectly and r equals about 0.874. Now, I don't know about you, but that whole process holds a lot of opportunities for errors. To reduce the possibility for errors, let's look at how to do this on the calculator. To find the correlation coefficient on the TI-83 or 84 calculator, you first need to make sure diagnostics are turned on. You do this by pressing the second button, then the number 0 to open the catalog. Then you need to arrow down until you highlight the diagnostic on selection. Click enter twice. The screen should say done. Now press the stat button, arrow over to the calc menu, then arrow down to or press 8, linear regression A plus BX is what it says. It will give you a chance to change X list and Y list to make sure you have them listed correctly. If you put those numbers into L3 and L4 or some other list, make sure that you change those. Then press enter as many times as needed to calculate. If you need to pause the video so you can get these notes down, you can do so. They're in your lecture notes as well. Okay, here is the problem we're working with. Old Faithful, located in Yellowstone National Park, is the world's most famous geyser. The duration in minutes of several of Old Faithful's eruptions and the times in minutes until the next eruption are shown in the table. Use a technology tool, you're going to use a calculator, to calculate the correlation coefficient for this data. What can you conclude? Okay, you're going to enter this data and notice that there are two columns each of X and Y. They're just put side by side here. There's a column of X and then Y and then another one for X and another one for Y. So pause the video to do this. Once you have done that, you should go through the process of getting the correlation coefficient that we went over before. You should have gotten the output you see here with an R result of about 0.979. This value suggests a strong positive correlation. As the durations of the eruptions increase, the times until the next eruption tend to increase. So we can state that it seems to be a strong indicator of a positive correlation. But what kind of scale or measurement are we using besides that it's close to 1? How do we determine what is close enough to consider it very strong? In your e-text, there's a table, Table 11, in Appendix B, called the Critical Values for the Pearson Correlation Coefficient. We need only find the absolute value of the R value and see if it is greater than the critical value on the table to decide if there's enough evidence to decide that the correlation coefficient rho is significant. It uses the N value of how many pairs, X and Y, and the critical values for alpha, 0.05 and 0.01. If the absolute value of R is greater than the amount that lines up with both of those, the correlation is significant. Otherwise, there is not enough evidence to conclude that the correlation is significant. This is what it looks like when you use the table. You determine whether rho is significant by looking at N and alpha. If the absolute value of R is greater than the value you come up with when you meet the alpha and N column and row together, then the correlation is significant. Otherwise, there's not enough evidence to conclude that the correlation is significant. Let's go over the process in words and symbols. First, determine the number of pairs of data in the sample, the N value. This is how many pairs of X and Y you have. Next, specify the level of significance, your alpha. Then find the critical value. This is where we use Table 11 in Appendix B. If the absolute value of R is greater than the critical value, we decide the correlation is significant. If it is not, then there is not enough evidence to support the correlation is significant. Lastly, interpret the decision in the context of the original claim. Using the Old Faithful data, you used 25 pairs of data to find R was about 0.979. Is the correlation coefficient significant? Use alpha equals 0.05. If we look at the table, we find the column for alpha equals 0.05. Then we find the N value row along the side, N equals 25, and find where they intersect, in this case at 0.396. Because the absolute value of 0.979 is greater than 0.396, you can decide that the population correlation is significant. There is enough evidence at the 5% level of significance to conclude that there is a significant linear correlation between the duration of Old Faithful's eruptions and the time between eruptions. Now, there's another method we can use to determine if rho is significant. We can use a hypothesis test to determine whether the sample correlation coefficient R provides enough evidence to conclude that the population correlation coefficient rho is significant at a specified level of significance. A hypothesis test can be one or two-tailed. Just like when we've used these tests before, the alternative hypothesis is the one that determines whether it's a left-tailed, right-tailed, or two-tailed test. If it's a less than symbol, it's a left-tailed test. Greater than is a right-tailed, and not equal to is a two-tailed test. Here's how it works. A t-test is used to test whether the correlation between two variables is significant. The test statistic is R, and the standardized test statistic T is found with this formula using R. T equals the ratio R divided by the square root of the ratio 1 minus R squared divided by N minus 2. If you'll remember, we said that degrees of freedom are lost with each identified variable. And we're dealing with an ordered pair here, so two variables. And N is the number of ordered pairs you're working with. So let's talk about the steps in words and symbols. We're getting good at these now, right? So first step for using the t-test for rho, we want to state the null and alternative hypothesis. Remember our rules for which is which according to the claim and which is the complement. Next, specify the level of significance and identify alpha. After that, identify the degrees of freedom, and remember you're dealing with 2 this time, so N minus 2. Then determine the critical value by using Table 5, the t-distribution table in Appendix B, and from there the rejection region or regions. Next, you want to find the standardized test statistic using this formula. Then decide whether to reject or fail to reject the null hypothesis. Lastly, we interpret the decision in the context of the original claim. So we're going to reuse the GDP data, but use tables to find our answer. So in this case, our N, or number of pairs, is 10. Our R value is 0.874. Alpha is 0.05. The alternative hypothesis is not equal to, so we'll be using a two-tailed test. My degrees of freedom is N minus 2, which will be 8. My alpha is 0.05, and I'm doing a two-tailed test. So using my table, I find the critical values are negative 2.306 and positive 2.306. The rejection regions are to the left of the negative 2.306 and to the right of positive 2.306. Using the t-test, the standardized test statistic is about 5.087. Now I compare this value to the critical values of negative 2.306 and positive 2.306. So 5.087 does fall within my upper rejection region. That means that I have the evidence to reject the null hypothesis. That means we favor the alternative, which is that there is enough evidence at the 5% level of significance to conclude that there is a significant linear correlation between gross domestic products and carbon dioxide emissions. Okay, we're going to end this video with a concept we need to keep in mind when dealing with correlation statements and variables. There are 4 questions we should ask when we find that two variables are strongly correlated. Is there a direct cause and effect relationship between the variables? Does X cause Y? Is there a reverse cause and effect relationship between the variables? Does Y cause X? Is it possible that the relationship between the variables can be caused by a third variable or by a combination of several other variables? Variables that have an effect on the variables being studied but are not included in the study are called lurking variables. Or is it possible that the relationship between two variables may be a coincidence? Is it possible that we are seeing things that we think are significant that actually are just coincidences? These 4 questions are really important to ask yourself before diving into the causation camp. Correlation is not necessarily equivalent to causation. There could be other factors at play in the background that could cause the relationship to happen. Okay, that's where we're going to leave it for this section. Good job. I'll see you in the next video.